Hello everybody, welcome back to my channel. Hope you're having a wonderful day so far. My name is Michael. We are jumping back into Harvard CS50x week 4 on memory. This is part 2 of the lecture.
All right, we are back in one erratum. So this was the line of code I proposed in CS50.h. It's not quite the line of code in CS50.h because, as was asked, stylistically, the quote-unquote right way to write this would indeed be without the space after the star. So even though string is not being declared as a variable here, but rather as a type stylistically, and I just asked style50 for the correct answer, it would indeed omit the space. So this is what I should have said earlier, and we'll fix that in the online version thereof. But for now, let's actually transition to taking a look again at the computer's memory and revisit some problems that we looked at indirectly over the past couple of weeks and better understand why things worked and now work the way they do. So let me go over to VS Code here, and I've written in advance a relatively simple program. I'm still using CS50.h and standard.io.h for this example. I'm calling getIn twice to get two variables, I and j, so two numbers from the user. And I'm checking for equality using equals equals. So if I equals equals j, I'm going to print same. Otherwise, I'm going to print different. So fairly straightforward, and it should just work. Indeed, if I open up my terminal window and I do, if I open up my terminal window, do make compare, because this file is compare.c, I can then do /compare and type in two numbers like 50 and 50, and they're indeed the same. Or I can do it again, 50 and 51, and they're in fact different. And I'll stipulate that pretty sure this code is in fact correct. But what if we make a change of sorts and actually compare not integers but strings? What's going on? Well, let's first consider what is happening with integers. So here's my computer's memory, and I've zoomed out a bit just so we can fit more on the screen at once. And here might be where I and j end up in the computer's memory when running this program. I here, j here, both of them 4 bytes, because both I and j are integers. It stands to reason then when I compare I and j, we are literally comparing 50 against 50 in that first scenario. And indeed, it's technically 32 bits and 32 bits, but they're exactly the same if they're both storing and representing the value 50. All right, so fairly straightforward. But what about strings? In fact, we deliberately introduced strcomp, or for string comparison, because when I last tried to compare two strings, it didn't actually work as intended when using equals equals. So in fact, let me go back to my code here and close my terminal window and just make a couple of changes here. Same idea, but different data type. So let's do string s equals getString. And we'll prompt the user for string s now instead of I. Then maybe a string t, just to keep the variable name short for the sake of discussion, and prompt the user for t here. Then let me go ahead and say if s equals equals t, go ahead as before and print out same \n. Otherwise, go ahead in my else clause and print out quote unquote different. All right. So same logic, but different data types, using strings for the type and getString for the function. Let me open my terminal window again, make compare. No syntactic errors, but let me go ahead and do /compare and type in something like, how about hi and hi, both in all caps, but they appear to be different. I can try again, maybe my name, David and David. It's also different, even though it seems to be the same. So what's going on? Well, you might already have an intuition, and someone last time when we looked at a program like this did have an intuition, but what if we make it more explicit now? What if I change my strings to literally char stars, which doesn't affect the functionality, but takes off one of those training wheels? I'm not going to get rid of CS50.h altogether, because as we'll see, I still want to use getString. Otherwise, it's a pain in the neck in C to get user input, but we'll come back to that. But s now is not only a string, it's more precisely the address of a character, technically the first character of a string. So what then is being compared on line 9 that's yielding this different answer? Why are hi and why are David different, even if typed identically?
They're in different places in
Yeah,
memory.
it's two different addresses. What's really going on, if we take a
on.
look at the computer's memory now, dealing with strings,
Survey
is
says
the following. Here's that grid of memory. Maybe s ends up here, and
Those are two
maybe
different memory
the
addresses. So you
actual
have to unpack
array
them
of
and
characters
iterate over
ends
them.
up here. Because notice when we're using strings, technically, we're storing the address and we're storing the actual characters. And that's all been happening magically in one step for us, one line of code. But technically, there's different chunks of memory involved. And it might be at 0x123, 0x124, 0x125, and 0x126. All of that happens automatically with that one line of code when I create and initialize S. Meanwhile, S is going to therefore store the address of that first character, hence the whole idea of a char star. But what is T? Well, maybe T ends up over here, somewhere in memory. Maybe the other hi that I typed in, or a bit later, the David that I typed in, ends up at maybe 0x456, 0x457, 0x458, 0x459. Again, who cares what the addresses are, but they are back to back to back, which is important. But suffice it to say, then, what ends up in T is the address of that second string that I actually typed in. And for all intents and purposes, that's like S pointing to this chunk of memory, T pointing to this chunk of memory. So when I use literally equals equals to compare the two strings, that is, compare the two char stars, that is, compare the two addresses, clearly they're in different places. It's like asking the computer, are 0x123 and 0x456 the same? Well, of course not. Those are literally two different numbers, written in hexadecimal or anything else. So we needed a solution for this, and that is why we introduced strcomp, the function that actually addressed this properly. If I go back then to VS Code here, and instead of using equals equals, I give myself access to our old friend now, the string.h header file. In that library is the definition, the declaration of strcomp. So I can do strcomp passing in two variables, s, comma, t. And recall, what is the return value I care about? What does strcomp return if two strings are equal? So it returns 0. Otherwise, it's a positive or a negative number, which helps with alphabetization. But that's not what we want here. I want to make sure that the return value of strcomp equals 0. And what does that do for me? Well, if I open up my terminal again, make compare, /compare, and again type in hi, exclamation point, enter, and hi, exclamation point, enter, now they're in fact the same. But if I type something different, like hi and bye, those, of course, are different, not on the basis of their addresses, but on the basis of their actual characters. And in fact, that's what's really happening. The way strcomp is implemented by someone else years ago is that they have some code, some kind of loop probably, that first dereferences S and T respectively, goes there, and then in some kind of loop iterates over these two strings in memory, checking whether the individual chars equals each other,
exactly
stopping
what
once
we
it
said.
hits \0 in
That's
either
exactly
string.
what I said.
And if they happen to look the exact same character by character, then it returns 0. It's a little fancier than that because it uses some less than or greater than to figure out if one comes before the other ASCII-betically. But it is doing the walking across this string. So the person that implemented strcomp uses a for loop, a while loop, whatever, to do all that legwork for us. All right, so if we now know and appreciate that these two addresses are indeed different, S and T, it turns out we can kind of play around with, create some new problems, but also solve them as well. So how might I go about, for instance, let's see, seeing what we just did. If I go back into VS Code here, let me just do something simple and no longer compare these, but just to make the point using our %p format code now, I can actually print out the actual values of S and P if I want to S and T if I want to convince myself of all of this. So I can print out, with %p with the value of S, with %p the value of T. And in this case, even if I type the same thing, watch again what happens. Make compare, /compare. I'll type in hi, and I should now see two addresses. But per the depiction on the screen, they do end up in different locations. They're similar locations. These numbers are actually pretty similar, but notice they differ down here. A B and an F puts them a few bytes apart, so they're actually next to each other in memory, but they're not, in fact, at the same location. So that's what's happening underneath the hood. And just to be super clear, it is rare, if ever, that you as a programmer will ever bother using %p to print out an address. Generally, we do not care where things are, just using it for the sake of demonstration, to make clear that we could go there if we so want. All right, well, what if we want to make maybe manipulate these strings and actually change them in some ways. Let me do this. Let me clear my terminal, close compare.c, open up a new file called copy.c, whereby I might ultimately need to make copies of strings in memory. And let me go ahead and do this. Let me include CS50.h, so I can still use getString. Let me include, how about standard IO.h, as we often do. Let me include string.h, as we now do. Int main void for my main function, and then in here, let's do the same thing as before. String s equals getString, and prompt the user for that string. Then let's go ahead and copy the string as follows. String t equals s. Then let's go ahead and capitalize the first letter of this string. And it might be a little hazy, but we introduced a library a couple weeks back called ctype.h, which has a bunch of functions related to types in C, one of whose functions, recall, is toUpper, which just uppercases a character. So what I'm going to do here is I'm going to change the first character of t, but not s, to equal whatever the return value of toUpper is, passing in the first character of t. So I'm just changing the first character of t to be the uppercase version thereof. Now I'm going to go ahead and print out the value of s is %s\n. I'm going to plug in s. And then I'm going to do the exact same thing for t, so I can see both the before and the after version of my capitalized change. Let me open my terminal. Let me do make copy. And I screwed up because I should be including not a C file, but a header file. So ctype.h at the top. Unintended mistake. Make copy again. That worked. /copy. And now this time, let me deliberately type it in all lowercase, HI exclamation point, because the whole point of t is to be uppercase. If I hit enter now, I see, a curiosity. Both s and t were somehow capitalized for some reason, even though I only changed on line 12 the first character of t. Why might that be?
My initial assumption is that because we have declared string t equal to s in memory, it is also at that location in memory. In Python, we would create like a new variable in memory, but in C, it's just referencing that same place in memory as a new alias called t. And so whatever you do to s will also be done to t and vice versa. That's my assumption.
What might that be? Let me offer a bit of a hint. What if, again, we take off some of these training wheels? S is just a char star as of today. T is just a char star after today. So what's happening such that I'm seeing that
they're at the same place in memory? Come on, Harvard students. Why aren't you getting this? I got this. Come on.
Change affect both
Put
S
me in
and
Harvard.
T? Yeah.
Come on.
Yeah, I'm really copying literally s and t, which means both of those variables contain the same address. So even though I'm following t's address, that leads me to the same location that s is pointing to. So I'm essentially changing the one and only one copy of high exclamation point. In fact, we can see that as follows. If I open up my computer's memory, let me propose that s ends up over here, maybe high and lowercase ends up down here, maybe at those same addresses as before, OX123. Therefore, s contains OX123. Meanwhile, t is a separate variable that I declared with almost identical code, but I then set it equal to s, which is like literally copying the value in s into t. If we now get rid of all these unnecessary addresses and just use abstraction, it's as though s and t are pointing at the same place. So it doesn't matter whether you follow s or you follow t. When you dereference either, as is implied by the square bracket notation, means go there, you're just changing the one and only copy of h. And so whether you print s or t, you print out the capitalized version thereof. So what's the solution here? Well, we actually need to be a little more clever when it comes to making actual copies. Up until now, super simple to copy integers, chars, floats, longs, doubles, all of those primitive data types, super simple because code like that on line 10 would just work. But whenever you're talking about something fancier like a string, which isn't one location, it's sort of a sequence of locations, someone's got to do the hard work of allocating another chunk of memory, copying the characters from old into new, and somehow keeping track of all of that. Now, we'll do this ourselves in just a moment, but thankfully, there's going to be a library that can make our lives easier instead. So let me go ahead and do this. Let me propose that we, in VS Code, improve this code as follows. Instead of just blindly copying s and calling it t, I'm going to actually use a new function called malloc. We haven't needed this before. It's among the remaining tools in our toolkit in C, but malloc stands for memory allocation. And it's a function that super simply lets you pass in as input a number. How many bytes of memory do you want? And it will hand you back a chunk of memory. Specifically, it will hand you back the address of that chunk of memory. Specifically, the address of the first byte of that chunk of memory. Free is the opposite. Once you're done with this memory, you can call free and give it back to the computer so that you don't eventually run out of memory. You can give things back when you're done. So how can I now leverage this in my own code? Well, let me propose that I implement a copy a little more cleverly here. Let me go back to VS Code here. And instead of using s equals t, let me instead say t initially should store the address of a new chunk of memory that's big enough to store the characters of s. The way I do that would be malloc. And how many do I need? hi exclamation point and the null character. I could just get away with saying 4. Give me 4 bytes of memory and store the address of the first byte in t. That is what line 10 is now doing. Now, that's kind of a stupid approach. Like, I shouldn't hard code the number 4, because who knows what the human's going to type in. But we have other friends here. We can say, figure out what the length of s is, add 1 more byte for the null character, and ask malloc for that many bytes. Because now, no matter how big or small s is, we're going to ask for the appropriate number of bytes. What is stored in t at this point in the story is the address of that chunk of memory. Specifically, the address of the first byte in that memory. Now, there's no null terminator or anything. Everything in there at the moment is sort of garbage value, so to speak, until I put something there. So what I'm going to do now is this. After I allocate that chunk of memory, I'm going to use a for loop, just like the authors of stir comp had, but for a different purpose. For int I equals 0, n equals the string length of s, semicolon, and we've seen that technique before, so we don't waste time calling Stirling again and again and again. I is less than n, and then I plus plus. And inside of my loop, I'm going to copy into location I of t, whatever's at location I of s, effectively copying from left to right all of the characters of s into t.
Yep.
At the very end of this, I could do something. But I think I could do something to manually add a null character to the end of my new string t, but I don't think I have to do that. The one time this makes sense is perhaps now. I'm going to actually iterate from I less than or equal to n, because I actually want to copy the null character as well. So if the string is hi exclamation point new line, I actually do want to go from 0 to 1 to 2 to 3 and then stop. Normally, I would go from 0 to 1 to 2, but I want to include this sort of secret null character there. So I think this for loop will capture that for me. I'm not going to change any of the rest of code. So all I have done that's different now is explicitly allocate a new chunk of memory for t and copy everything in s into t. But to use malloc, I need a new library. I'm going to go up here and include standard lib.h. And again, you learn through practice what's in what library, or you can go to manual.cs50.io and just look it up to figure out where, in which header file something is. And I'm also going to include the same header files as before. So the only change is to add standard lib. Let me open my terminal window, make copy, /copy, and now let me type in hi exclamation point in all lowercase, and I should see in a moment the output of both s and t, but hopefully only one of them is capitalized t. And indeed, I've done it somehow. So what actually just happened? Well, if we actually go over to a visualization thereof, here is my computer's memory when s exists. If, though, I'm going to allocate new memory with malloc, that's like calling malloc, getting some chunk of memory. Maybe it ends up here. Maybe it ends up somewhere else. I'm just keeping it in the same place for discussion. And the first address happens to be 0x456. Well, what gets stored in t? The return value of malloc. And malloc returns the address of the first byte of memory. So what ends up in t is effectively 0x456. But who cares? We'll just draw it abstractly as an arrow. What does my for loop then do? Well, it iterates over s and t in lockstep, such that the h gets copied, the I gets copied, the exclamation point gets copied, and because I use less than or equal to, we also copy the secret null character as well. Then I use 2 upper on t bracket 0. Here's t bracket 0, and so I think only the h in t is now capitalized. It's not a particularly interesting exercise, but it does demonstrate, really with as few steps as possible, how we can solve this problem of actually copying strings in memory by allocating enough space for them in that actual memory. But there is a caveat. A lot of things, unfortunately, this week onward can go wrong when it comes to memory. Like your computer could be out. Maybe you have an older computer. Maybe you have a really fancy program that has so many variables, so many arrays, that eventually you run out of memory. It's possible that malloc can fail. Something can go wrong, and malloc will not, in fact, return to you the address of the first byte of memory available, because if none's available, it's got to return something else. So in cases of error, what malloc really returns to you is 0. Like, I have no valid bytes for you. And 0 itself is a number, so that's a little confusing. And this doesn't really help with confusion. What malloc returns if an error happens is null with 2 L's. This was a stupid design decision decades ago to call the character 0 NUL and the pointer 0 NULL, but this is where we're at. So NULL is the address 0, and it almost always signifies something went wrong. We just need a special symbol to signify something went wrong when returning a value from malloc. So how can I use this? Unfortunately, now, just like in some of the problem sets thus far, when you've started to add error checking to when things can potentially go wrong, your code gets a little more verbose. But what I'm going to do here, if I go back to VS Code, is the following. What can go wrong? Well, if t ends up equaling null, that is, if it has a bogus return value in it that is not a valid memory address, then there's not much I really can do except like return 1 just to signify error. I could print out an error to the screen. I could inform the user somehow. But if malloc returns null, I had better not proceed to try copying things from left to right into it, because there is no memory there. That chunk of memory on the screen at bottom right does not exist if malloc fails, of course. So you don't want to go there and start blindly touching memory, let alone capitalizing memory that's there. So I have to start adding in some of these error checks in this case. And in fact, even this is a little naive. It's probably not safe to even assume that the user typed in any string at all. Maybe the human, just to be difficult or making a mistake, and just hit enter. So the length of the string is 0. You probably shouldn't try capitalizing 0 either. And so what we should probably do down here, too, to be super safe, is only if the str length of t is at least greater than 0, then go ahead and capitalize it. Otherwise, do not touch that memory either. In other words, starting this week and next week, and even when we get to Python, you should start acquiring an instinct to code defensively. Things can go wrong in your code, in someone else's code, and if you do not handle those situations with ifs or else ifs or the like, your computer will crash, the thing will freeze, or the like. And again, to tease the CrowdStrike example, if you screw up and you don't check the boundaries of something, the length of something, who knows what can happen? Because if you touch memory that does not belong to you, the typical behavior, again, is to crash, to freeze, to do some undefined behavior like that. Now, I will say, this is getting really annoying. I mean, I've written, what, like 30 some odd lines of code just to copy 2 strings. That's a little unfortunate when this is probably a pretty common thing to do in the real world. So it turns out there are library functions like this, too. And in fact, I can get rid of a lot of my code here for copying. And I can actually just call a function, strcpy, strcpy for short, and pass in the destination, pass in the source, semicolon, and that will do all of the for loop or the while loop or however that person implemented it of copying one into the other. The ordering is a little weird. It is indeed destination, comma, source, but that saves me the trouble of doing all of that code myself. A really good question. Let me summarize. If you allocate 2 variables that happen to be next to each other in memory, but maybe you type in, a very long string for one of them, can one overflow into the other one? Short answer, yes. And we're going to talk about that briefly today. The code I've written is not vulnerable to that at the moment. And in fact, among the things that getString has been doing for us since week 1 is it actually sort of crawls over the user's input, literally taking like baby steps to make sure that we only allocate more memory for every keystroke that you type in. So theoretically, there should be no way to crash getString unless you type in more bytes than the system has even memory for. But even that, we should be able to detect because we are somewhat inefficiently but very conservatively trying to avoid the situation you described. But it is too common in life, as again, with CrowdStrike, you'll see that humans will make mistakes when it comes to the length of memory or arrays that we have. Now, I alluded to there being one mistake or omission here. Did I somehow not practice what I preached a moment ago about malloc and its cousin? I never freed my own memory. So technically, this program has what we would call a memory leak, whereby I'm asking for memory on line 11 via malloc, but I'm never giving it back to the operating system. Now, this is a bit of an overstatement because technically when the program quits, it should automatically give everything back. But a lot of programs in the world keep running again and again and again, really forever, like a clock program or a web server or an email server and the like. And if that code that you or someone else has written asks for memory, and never hands it back, freezes, crashes eventually because the computer will somehow run out of memory. So it's an easy fix. At the very bottom of this program, once and only once I am done using T in the first place, I can simply free T. And C itself, or really the functions that we're using, keeps track of how many bytes you asked for. You do not need to. When freeing it, it will free that byte onward that you requested. So free sort of does the opposite of then malloc. All right. Unfortunately, we have so much power at our disposal now, lots of things can go wrong, but thankfully there are tools that help you find these mistakes so that if and when your program crashes, you don't have to just kind of stare at the screen or ask a TF or another human for help. You can actually use software tools that other people wrote that detect these common errors. And one of these programs that you're now going to have access to, besides printf, besides debug50, besides the rubber duck, is a program called Valgrind, which is a command line program whose output is a little scary looking, but it will allow you to look at your program for memory-related errors. So let me go ahead and propose this. I'm going to open up a program that I wrote in advance here called memory.c. And quite simply in VS Code, it looks as follows. I have including standard I/O, I'm including standard lib, so that I can use malloc. And this program does nothing useful. It just demonstrates as simply as I can a bug. On line 6, I'm allocating a variable called x that's going to be a pointer to an integer. And I'm allocating space for 3 integers. So we haven't seen this before, but it just kind of does what it says. Give me memory for 3 of these things. What are these things? Well, whatever the size of an int is, I know it's 4 usually. So I could just write 4 times 3, but I'm going to generalize it. Size of is an operator in C that lets you figure out what is the size of this type of variable. It's usually 4, but on older computers, eventually on newer computers, it might not be 4, so I'm not going to write 4. I'm going to say size of int. So this whole line 6 gives me enough memory for an array of 3 integers. And it stores the address of the first byte in a variable called x. So what's x1 going to be? 72. What's x2 going to be? 73. What's x3 going to be? 33. Even in these 4 lines of code, there's 2 bugs. Can you spot any of them? Yeah. What's that? Yes, so I did not 0 index my array, so that's sort of week 2 type mistake. This should be x bracket 0, x bracket 1, x bracket 2. And there's a second, more subtle mistake. Yeah. I don't have what? I don't have room. Oh, I don't have room for the 0, but that's OK because I'm dealing with integers only. I'm not strictly trying to treat this like a string, but good eye, but only relevant if I'm dealing with strings or char stars.
So there's bugs here?
It's subtle, but we also talked about it like 3 minutes ago. Yeah, I didn't free the memory. So I called malloc, but I didn't eventually call free at the end of my function. So at least 2 mistakes, it would seem. Now, you can reason through this, and there's only 4 lines of code, so eventually you'd probably figure it out with some time and practice. But could a program help me spot these mistakes? Well, debug50 is not relevant here per se, unless your program crashes. Debug50 can probably tell you on what line it crashed, but not necessarily why. What we need is a memory-related program called Valgrind, and to do this, to use it, I'm going to do the following. I'm going to run make memory, And if I do /memory, at a glance, nothing seems to go wrong. It didn't even crash, but it's still incorrect. And especially if I have these kinds of bugs in larger software, it's definitely going to crash eventually. So let me do this instead. Let me run this program called valgrind on /memory. So just like you run debug50 on /something, you run valgrind on /memory. Let me increase the size of my terminal window, because there's going to be a lot of ugly output here for a moment, and hit enter. And you'll see a whole bunch of cryptic output and a lot of numbers which largely aren't useful for us until we get to the error messages. So I ran the command up here. I saw all this crazy output, but what's germane? Well, here I have invalid write of size 4. It's a little technical, but that just means I'm changing something that involves 4 bytes. Well, what does that mean? Well, apparently my mistake is in memory.c, line 9. And it's elaborating with some cryptic addresses, which, again, I don't really care about. But I do care about this. After a block of size 12 is allocated, so there's 12, like evidence that there's indeed an array of 3 ints, which total 12 bytes. So that's consistent. But what's going on? It's at line 9. Well, how did I somehow touch 4 bytes that I shouldn't? Well, if I go back to my code by shrinking my terminal window, look at line 9, it did not like, as you observed, the last element of the array, because I 1 indexed instead of 0 indexed. So OK, I think my fix is going to be to change this to 0, 1, and 2. So 0, 1, and 2. But let's go back to the errors, because there was another one on the screen. If I ignore anything I don't really understand in this summary, here's something. 12 bytes in 1 blocks are definitely lost in loss record 1 of 1. More verbose than ideally it would be. But that problem seems to relate to memory.c, line 6. So I'll admit, valgrind's output is sort of a big, complicated mess. But there are little hints of diagnostically useful information, like invalid write of size 4 and the line number of the file. 12 bytes in 1 blocks are definitely lost in memory.c and line number. So those are the kinds of things you want to look for, even if at a glance it is and will look confusing. So let me go back to now line 6. And oh, line 6, even though it's not obvious what's wrong with this line, if I'm somehow losing 12 bytes, well, it must be a memory leak. So let me just have the intuition to go in and say, oh, eventually I have to free x, because x is pointing at that chunk of memory. Let me now clear my terminal window down here, make memory again, /memory. And it doesn't seem to crash still, but it is more correct, even though at a glance it seems fine either way. Let me do now valgrind of /memory. Let me increase the size of my terminal window, clear the screen, and hit enter. And now there's slightly less output. But what I really like is the sound of all heap blocks were freed, whatever that means. No leaks are possible. And even though there's still a lot of output there, I don't see anything glaring anymore. So valgrind 2, this week and next week, will be your friend. And all it's doing is helping check for memory-related mistakes in your code. All right, well, let's play around slightly more with these garbage values to which I alluded earlier. Let me actually close this. Let me code up a file called garbage.c, just so we can make the point that there can be these so-called garbage values in a computer's memory that are really remnants of something else that has been at that location in memory before. And I can actually do this pretty easily. Let me, in garbage.c, include standard io.h. Let me go ahead and do standard io.h. Let me go ahead and do int main void. Inside of my main function, let me just give myself an array of like a lot of scores to come back to like week 2 when we introduced arrays. Suppose I very sadly have 1,024 scores to keep track of over the course of college. I now might iterate over those as follows. For int I equals 0, I is less than 124, I++, and then inside my for loop, let's just blindly print out those values, %i, \n, scores, bracket I. The problem, though, is that I have neither hard-coded those actual scores into this program like we did in week 2, nor have I prompted the user for the scores with getInt or anything else. So who knows what I'm going to be printing 1,024 times? Well, let me open my terminal. Let me do make garbage. Sort of pun intended. Let me increase the size of my terminal window, /garbage, and I should see 1,024 values that eventually will be my scores, but who knows what they are now. Enter, It's a mix of some really good and some really bad scores, it would seem. Some zeros, some small numbers, some big numbers, my God, some negative numbers, which isn't good for scores, but they're all over the place. And if I scroll up, I could count them. There's indeed going to be 1,024 of them. But they're garbage values in that I can't make head or tails of what they actually are. As an aside, this has nothing to do with C, but the operating system, Linux, that we're using here does have commands that you can run if you are getting overwhelmed by output. So for instance, if I run garbage again, if there's going to be more output than you can see at once, and you don't want to have to bother scrolling back through time, you can actually do what's called piping it to a program called less, which, as the name suggests, will show you less of the output at a time, one screenful at a time. So if I hit enter now, I only see the first screenful until I hit space, 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 and so forth, and it will paginate the output for me, and I can just hit Q when I'm done with that. So it doesn't change my code, doesn't change my program, just a handy command line trick if you're ever overwhelmed by the amount of output there. But these garbage values can really get us into trouble. And in fact, let me propose to consider another program that's a little arbitrary, but it's going to use some of today's building blocks. So here's a main function. And at the top couple of lines here, I'm doing this. I'm creating a variable called x that's going to store the address of an int. I'm creating a variable y that's going to store the address of an int. So far, so good. I haven't assigned them any values yet, but that in and of itself is not problematic. I can always assign them values later, like any variable. I'm now going to allocate enough bytes for the size of an int. You and I know it's probably going to be 4, but I'm doing it dynamically, asking for the size of an integer. And I'm storing the address of the first byte in x. But notice what I'm not doing is storing anything yet in y. The next line of code here, I'm sort of using the sentinel value 42 and storing that at the location in x. So the dereference operator says, whatever address you got from malloc, go there and put the number 42 there. This next line says, go to the address in y and put the number 13. We haven't given y a value. I didn't copy s's value. I didn't malloc anything for y. It contains a garbage value. Maybe it's 0 like we saw on the screen. Maybe it's a really big number. Maybe it's a big negative number. Who knows? But that's like saying go there and like put this number 13 in some random unlucky location. And again, program's probably going to crash, freeze, or something else. The other lines here are OK. Eventually, I get around to copying x into y, giving it a valid value, and then going to y's value and assigning it the number 13. So that one line of code was the problematic one ultimately. So what's nice about this code is that it actually happens to line up perfectly with a fun video that our friends at Stanford University put together that's about 2 minutes long, and it introduces a character that's well known in computer science spaces as Binky. So Professor Nick Parlante of Stanford spent some time doing some claymation to bring exactly that code and exactly that problem to life if we could dim dramatically the lights. All right, so Binky's purpose in life is really to make clear that bad things can indeed happen when you touch memory that you shouldn't, including things that we now know as garbage values. But there's even other problems, but also solutions that we now have access to, thanks to our newfound understanding of memory and, in turn, pointers. So it's been very common over the past few weeks, especially last week, to have to swap values. Like when we were doing bubble sort or selection sort, we kept having our human volunteers swap locations. And in the computer's memory, or in our pseudocode, we had to have 2 variables or 2 values swap locations as well. For this, we thought we'd motivate folks. We can offer you either a little Mario mushroom or question mark if we can get one more volunteer today to act a little something out with me here. Don't all raise your hands at once. How about, I saw the Harvard shirt, is it? Or that shirt, yes. Yeah, no, you, yeah, come on down. Where we have 2 glasses of water, one is pink, one is blue, and each of these effectively represents like a variable that contains some value, either pink or blue. Could you go ahead and swap the 2 values of these glasses? OK, that's technically just like moving the variables around in memory, but I'd really like you to get the pink water in the blue glass and the blue water in the pink glass instead. So let me undo that.
Oh, come on, what are you going to do? Mix them together?
You're hesitating, why?
Because if I pour the blue in the pink, then they're going to blend together.
Yeah, and you're going to sort of overwrite the value with the other. And so we're going to lose information in that case. OK, so this was a bit of a setup. So let me get you a third glass, or a temporary variable, if you will. And if you want to verbalize how you would solve the problem now with this third variable.
OK, so I'm going to pour the blue into the new variable, and then pour the pink into my old blue cup.
Nice.
and then pour the blue back into the old pink cup.
Very nice. I think that warrants a round of applause, if we could. OK, nicely done. Thank you. OK. Which would you like?
This one.
All right, so thank you to Gabe. So all right, this was all to make the point that swapping is not that hard, and we all have kind of an intuitive notion of how to do it, but we do need, it seems, like a temporary variable. And that actually maps pretty cleanly onto C code. So how might we do this in practice? Well, if we wanted to implement an actual function in C that does swapping, for instance, I might do, if we want to actually do something in C that involves swapping, I might do something like this. A void function, because I don't need to return a value. I just need to do some work. Function's called swap. It's going to take in two values, int A and int B. And the goal in life here is to swap A and B. It's actually pretty straightforward. I could actually do lines of code like this, calling A and B the two inputs, like the pink and blue glasses, temp, or TMP for short, for the temporary variable. And just as Gabe did, I can store in the temporary variable one color of liquid, or the value of A. I can then change A to be that of B. And then I can copy the value from the temporary variable to B, and at which point I don't care about temp anymore. This code is correct. It would swap those values just as Gabe did with the glasses of water. But it's only going to work inside of the scope of swap. And this is the catch. Recall that when we introduced the notion of scope earlier, a few weeks back, we said that variables really only exist in the context of the curly braces in which they're defined, or in this case, as part of the arguments passed into the function. So this successfully swaps A and B. But if main or any other function is using swap, it's actually not going to have any useful effect on the original values of A and B. In fact, let me go over to VS Code here, where while Gabe was doing that, I whipped up this program in advance. And it looks like a lot, but it does something relatively simple. I've got main, which declares two variables, x and y, values of 1 and 2. I'm then just printing out x is this, y is that. I'm then calling a swap function. And then I'm just printing the same thing. X is this, y is that. The whole point being, hopefully it'll say the opposite the second time. What is the swap function? Exactly what I just proposed earlier, which is exactly what Gabe just did correctly with the glasses. But as you might see where we're going with this, if I go into my terminal window and say make swap, /swap, enter, it doesn't actually seem to affect the values of x and y. It does affect the values of A and B. And I can see this if I use our old friend debug50. Let me go ahead and set a breakpoint inside of swap. Let me run debug50 on /swap, enter. And just to demonstrate what's going on here, let me step through a few of these lines of code as follows. So notice one at top left. Temp has some bogus value initially. It's a garbage value. It's like putting some random color inside of the glass, but I kept it empty because in the real world, we need space for the colored liquid. But A is 1 and B is 2. Why? Because we passed in x and y respectively. If I now step over line 17, notice that temp changes to 1. If I step over line 18, A changes to 2. If I step over line 19, B changes to 1. So A and B, per Gabe's algorithm, were swapped correctly. But if I continue running this program all the way to the end, ultimately I got, because of this second printf, that x is still 1 and y is still 2. So A and B were changed clearly per the debugger, but x and y were not. So why is that? Well, it turns out that the answer to that, too, relates to memory. And code like this, at least if encapsulated in a function, is not correct, precisely for the matter of scope, because we're changing the values of variables that are local to the swap function, but has no effect on main that's actually using this function. And the reason for that is a term of art. When you pass arguments to functions, you're generally passing things by value. You are passing in copies of those values. So when you pass in x and y, you're really passing in a copy of x and a copy of y that you can do anything you want to, and we're calling them A and B in the context of swap, but that has no effect on the original versions of x and y. What's really going on, though, can be thought of again in terms of the computer's memory. So here's a chip of memory. Let's kind of zoom in and abstractly on the sort of grid as we keep describing this, and consider that we can use this memory in bunches of different ways, but the world has standardized how we use computers' memories when running programs. And we tend to use this part of memory at the top, so to speak, in certain ways, and this type of memory at the bottom in other ways. And if we understand what those ways are, we can actually infer deductively why this function is not working as intended. So it turns out, let's say even get rid of the individual bytes, because we don't really care about numbers for now. It turns out that when you double-click a program on your Mac or PC, or tap an icon on your phone, or run /something on your code space, the computer automatically loads the program's machine code, the zeros and ones that someone else compiled, or maybe you compiled, into the top of your computer's memory, so to speak. It's not literally the top, because who knows how the thing is oriented, but just for the sake of discussion up here. What else gets loaded into the computer's memory? If your program has any global variables defined outside of main, by convention, they go below the machine code that was loaded into memory. What else? If you end up using malloc in your code, that memory comes from this location here, which we didn't do until today. But actually, it turns out that getString has been using malloc all this time since week 1, because that's how we're getting an arbitrary amount of memory for everything you might type in at the keyboard. The heap, though, so to speak, grows downward. So the more and the more and the more and the more you call malloc, the more stuff that gets filled up top to bottom in the so-called heap. But there's one last region of memory, generally called the stack, much like a stack of trays in the cafeteria or dining hall, that sort of works its way up as you continue putting stacks, tray and tray and tray on top of each other. The stack, so to speak, grows upward. And the heap and the stack are used differently. The heap is indeed used for malloc, but the stack is used anytime you call a function. Anytime you have local variables, they use memory down here. So in particular, for the code I just wrote a moment ago, where I had a main function and a swap function, the stack gets used to implement this kind of logic as follows. I first, unbeknownst to me, my computer does this for me, I get a chunk of memory at the bottom of my computer's memory space that contains any command line arguments, if we had int argc and char and string argv, like a couple of weeks back, or if I have any local variables like x and y. If I then call a function like swap, swap gets its own chunk of memory, its own frame of memory above main in the computer's memory. So it's like putting down a main tray from the dining hall and then a swap tray on top of it from the dining hall. Each of them contains their own local variables, x and y here, a and b here. And you can kind of see where this is going already. If x and y live here, but we're changing a and b here, well, obviously we're not changing x and y down here. Well, let's be a little more specific. In the main function, when I have two local variables like x and y, it's like having space for them in the computer's memory. And initially, I had values 1 and 2, respectively. When I then called a swap function, that had two local variables of its own, technically arguments, passed in, which, because I'm passing by value, gets copies of x and y called a and b. But the values are going to be the same initially, 1 and 2, respectively.
OK, so is he getting to that we have to pass in the memory address of those values, or the pointers to those memory addresses, unpack the value there, or dereference the value at that address, do the swap, and then we can do it? I think he's trying to allude to that we need to actually pass in the memory addresses of those physical variable locations at that scope. Or maybe there's some sort of other functionality that happens in between.
But then in the 3 lines of code that represent what Gabe did with the glasses of water is we have a temporary variable, a third, still in the same frame of memory. And I assigned with this code here, let me
People are saying I'm right in the chat. Let's go. Man, we are getting this. Feels good.
Step out of the way. This first line of code stored the value of a in temp, like this. The next line of code stored the value of b in a, like this, at which point, unfortunately, they're identical, but no big deal, because like Gabe, we kept the temporary variable around. And then we can store the value of temp inside of b. Now, as an aside, with respect to the debugger we pulled up earlier, as well as a couple of weeks back, when you've looked at the top left of the debugger window and you can see your local variables, what you're seeing in the debugger is either these variables if you've set a breakpoint in main, or these variables if you've set a breakpoint in swap. The debugger is just showing you what variables are in scope. What does scope really mean? It's a slice of memory at that moment in time, effectively. And we've been simplifying it verbally by saying what's between the curly braces.
So do you access the heap then? Does the stack, like, so at some point, like, reach the heap? Or how does it interact with the heap?
But that's the simpler way of describing really this. Now, we don't care about temp eventually. What we do care about is having swapped these values. But unfortunately, as soon as swap returns, well, mains x and y are literally left unchanged because we only passed in copies thereof. So the fundamental problem seems to be that the swap function is logically correct, but it has not been given access to the locations of x and y in memory. What swap really needs is a treasure map, so to speak, that leads it to the actual location of x, the actual location of y, so that using like the star operator, it can go there and swap the actual values inside of mains frame of memory. So what we really want to do is what computer scientists would call pass by reference, or pass by address would be the same thing in this case, whereby what I want to do is not this code per se, which is logically correct, but doesn't fundamentally change the caller's variables, x and y. Watch the delta here. This is correct. And it looks crazy scary at a glance because there's all this new syntax, but it's really just the same syntax from the start of today used a few different places. What I'm saying now in this correct version of swap is that A is not going to be an int per se. It's the address of an int. And B is going to be the address of another int. This is my sort of treasure map whereby A and B are going to contain the addresses of x and y. What am I going to do? Well, temp is still just an int. It's still just an empty glass. But if I want to store the value at A in temp, I have to go to A and store it in temp. I have to go to B and go to A and put the latter in the former in the latter. I have to the first and the second. Then I go and get the value of temp and put it at the address in B. So exact same logic, exactly what Gabe did, just way more syntactically involved. But again, it's just using pointer declarations up here and pointer dereferencing down here to go to those locations in memory. And in fact, if I make this change in my own code here, let me go back to VS Code and let me hide my terminal. Let me make these changes. So pass in the address of an int, the address of an int, dereference A, dereference B, dereference A, and dereference B. It's almost done, but I do have to change one more line of code. And based on what we've discussed thus far, how does line 11 need to change? I no longer want to pass in x and y.
You need to pass in there
the address of x and the address of y, which involves the syntax ampersand x and ampersand y.
We are killing
so
this
syntactically
lecture.
way scarier than it once was, but it's just these simple building blocks. Get me the address of x, and then go to that address as with the star operator. So let me open my terminal window again. Let me do make swap enter. It's erroring now, but why? I've made a subtle mistake. It doesn't like the fact that I've passed in the address. But wait a minute, let me scroll up. What else needs to change? The prototype here. So this also needs to be matching the actual implementation. So sort of newbie mistake, but I think now if I do make swap again, does compile, /swap, I should see x is 1, y is 2, and then hopefully, indeed, the opposite. So this version of swap correctly swaps the value because now I have a correct understanding of what is going on inside the computer's memory. And indeed, if we look at this code now in the context of the stack frames, let's see what now happens. So here is, again, the same setup. Main has variables x and y equaling 1 and 2. Swap gets called, but what are A and B? They're no longer the values of x and y, but the addresses of x and y. I don't care what those addresses are, so I'm going to abstract it away with some simple arrows. But these are sort of like the treasure map I keep referring to, the breadcrumbs, however metaphorically you want to think of it. A and B now lead to x and y. So you're passing things in by reference, so to speak, and therefore swap can manipulate those values. Now, as an aside, pass by reference is really the same idea as pass by value, but the values you're passing in are the addresses instead of the actual values. So it's sort of just context dependent as to how you think about that. But passing by reference means really you're passing in by address. All right, so with that said, step by step, what's happening? I'm going to A, which is going to contain the value 1, and I'm going to store that in temp. So what I should see in temp still is 1. Now I'm going to go to B, and what I should see at B is 2, and I'm going to put it at star A, which is the same thing as 2 here. Then lastly, I'm going to grab temp, which is 1, and I'm going to put it at B, which is like following that arrow and changing that to 1. And this then pictorially is why my new version of the code indeed works as expected. And better still, when swap is all done and that frame of memory is taken away. It's still physically there, but we don't care about it anymore, so we might as well think of it as just disappearing. The change has, in fact, permanently affected main's version of x and y. So here then, to recap, the bad code, but logically correct, just doesn't get the job done. The green code, of course, does get the job done for exactly those same logical reasons. But there's another problem we've now created. Even as we understand how the stack's working, and I claim that the heap is where malloc takes memory from, having like two arrows pointing at each other does not seem like a very good design, right? Because if you keep using heap, 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 heap by calling malloc a lot, you're going to eventually overflow the stack. Or if you call lots and lots and lots and lots of functions, as you might with recursion or some other technique, you might overflow the stack, like a big stack of trays eventually kind of toppling over and touching things that it shouldn't either. Unfortunately, there's no real solution because you only have a finite amount of memory, so it doesn't really matter if things go this way or this way. Eventually, you're going to either run into other chunks of memory or run out of memory altogether. So strictly speaking, this isn't such a bad thing unless you let things get out of control and you don't keep track of how much memory you're using, or defensively make sure you're freeing it as much as you can. And there are terms of art out there like heap overflow, which means if you call malloc too many times, you might somehow overflow some other area of memory with the heap. Some of you might know a popular website called Stack Overflow. Well, what is the etymology of that website? Stack Overflow is when you call so many darn functions that they overflow each other and maybe hit the heap or overflow each other in some way. You're overflowing the memory region known as the stack. These are generally examples of what are called buffer overflows, where buffer just means a chunk of memory that you're using for some purpose. And so a buffer can certainly overflow another, especially if you're treating it as a chunk of memory this big, but you start poking around past the end of it. It's like allocating an array for 4 characters, but trying to print the 5th, or the 6th, or the 100th, or the 1000th. If you've not asked for it, you're overflowing the buffer you've been given. So an array is just a buffer. And YouTube and Netflix, they all have buffers in the colloquial sense, in that they might pre-download a few seconds or minutes of video, storing it in a chunk of memory, like an array, or maybe somewhere on the heap. But the point is, a buffer is a finite size, and you can potentially overflow it by going past the boundary of it, past the end, or maybe even past the beginning. And thus was the issue with the real world a few months back with CrowdStrike. So this is very popular security-related software, ironically, that a lot of the world has installed on their servers to keep themselves safe. For those unfamiliar, unfortunately, this very software crashed some months back, taking down very important systems with it, including Delta Airlines' site and so many other companies. And this cost the world millions of dollars probably in lost labor and effort because systems went down, sales were lost, human time was incurred, and it boiled down in retrospect to the stupidest of bugs, if I might say. If you read through their very long PDF, their postmortem that describes what exactly went wrong, which took a few weeks, I believe, to come out, there was this paragraph here, which actually sounds like a lot of big words. Sensors that received the new version of channel file 291 carrying the problematic content were exposed to a latent out-of-bounds read issue in the content interpreter. The real interesting part is the last sentence. The content interpreter expected only 20 values. Therefore, the attempt to access the 21st value produced an out-of-bounds memory read beyond the end of the input data array and resulted in a system crash. So literally, even though you're only in a class like this for a couple of months' time now, they had an array of size 20, and they wrote code that tried to access the 21st element. They touched memory they shouldn't have. The software froze or crashed. Therefore, the systems that froze or crashed and cost the world millions of dollars in downtime and other side effects because of one off-by-one error. So it's a very possible danger to trip over, and among the downsides of languages like C is that they make it very easy to do this. There is nothing in C stopping you from doing this, and a few other languages allow this as well. Other languages like Python and Java generally prevent you and me from doing this. Why? Because humans for years were writing so much darn buggy code that we realized, wow, we should probably build into the programming language defenses against this stuff. So with the right language and the right know-how, you can avoid these problems altogether. But in this particular case, they had code that similarly was not sufficiently tested. They didn't have a check 50 to tell them a priori whether or not the code was correct. And so they shipped this to computers around the world. As an aside, too, this is one of the dangers of automatic updates. If you have this on your phone or your Mac or your PC, let alone your corporate servers, if you update automatically your systems, but the update itself is buggy, you can therefore take down your whole system, personally or professionally. There's a lot of real-world implications to that business decision they made, it seems, to update so unilaterally as well. So beware, but these things happen very really in the real world. OK, so let's take things down back to sort of like CS50 land here. Here was the functions, the training wheels that we've been using since week 1. And let's just consider for a moment how one of the most powerful of these does. Let's consider for just a moment how one of the simplest of these actually works, namely getInt. So it turns out in C, it's not that hard to get an int or a char or a float. Relatively simple, at least in a safe way. Strings are the scary one, because who knows how many characters the user is going to type in. And you would seem to have to decide in advance, do I want room for 1 character, 4 characters, 100, 1,000? What if I get the number wrong and they type in a really long paragraph? Ints and chars and floats are easy because they're 4 bytes or 1 byte or 4 bytes. You sort of know in advance. So let me propose that we implement a simple program that really kind of implements the idea of getInt. So first, let me open my terminal and clear it. Let me open a new file called get.c, because I'm going to implement my own functions for getting input. I'm going to go ahead initially and actually still use CS50.h, and I'm going to use standard.io.h. And then in main, I'm going to go ahead and very simply, as in week 1, do this. Int n equals getInt, and just prompt the user for n. So nothing interesting there. And then quite simply, I'm going to print out using %i, the value of n, passing in n. So again, week 1 stuff, no memory, no explicit use of memory or pointers here yet. Make a get, /get, type in 50. Program for now seems to work. But suppose I take away truly the training wheels, not just for the keyword string, but for the getInt function as well, and I take away this header file, which means getInt no longer works. How could I implement this instead? Well, without CS50's training wheels, you can still solve this problem. You can declare an int called n, and don't give it a value initially because you want it from the user. I can then prompt the user with like a printf n : space with no new line, because I just want a blinking prompt for the user, which getInt does for you automatically otherwise. And I can use a function called scanf to sort of scan the user's input for some format string. So for some type of formatted text. Maybe it's an int, a float, a string, or something else. So scanf is sort of like the opposite of printf. Printf prints something, scanf reads something from the user themselves. All right, so how can I use this? I can call scanf. I can say, what do I want to scan from the keyboard, so to speak? And I want to scan in an integer from whatever the human types. Where do I want to put that integer? Well, I can't just say put it in n, because you can't change. I want n to persist. I want to tell it to go to the address of n and put it there, wherever there actually is in memory. So again, just like with swap, if I want another function to be able to change my variable, can't just hand it the variable. I have to hand it the address of my variable. And scanf is designed to expect that. Now, as my last line, I can print out n : %i \n, and now print the value of n. So it's a bit of more of a mouthful. I've got like 2, 3 lines instead of my 1 with getInt, but I think it'll work. Let me do make get, /get, and type in 50, for instance, enter, and it does seem to work. And effectively, this is what getInt is doing. getInt's a little smarter because, for instance, if you don't type an int and you type in cat or dog or bird or something else, like weird things will happen. So we make sure that if you don't type in something that's actually an int, we prompt the user again and again and again using our own loop. So we sort of handle that error checking for you. But if I want to do this with a string, how might I go about doing this? Well, let me go back into my program here after clearing my terminal. And let me just kind of do the same thing, but with strings. I could say string s, but we know strings don't really exist as a data type. So I'm going to more explicitly say char *s. Like that's effectively a string, or a placeholder therefore. Let me print out a prompt for that string. Just say s:, just because I want the user to type in a string for me. And now I'm going to use scanf again. What do I want to read from the user? Well, I want to read a string. And so just like printf, I use %s to scan a string from the human's keyboard. And now, after that, I need a place to put it. Well, I think I want to put it in my string s. I don't need an ampersand here because s is already a char *. It's already the address of a string, if you will. But now if I go and print this, I'm going to say s, %s, \n, just as before. So it's the exact same logic, but this line of code is now dangerous. And this is why we give you getString, and this is why more of the world should use libraries instead of doing this. Why is this line of code on line 7 dangerous or undefined, what it will do?
You're trying to save in a single memory location a bunch of characters.
It doesn't know where my string's going to end, or more specifically, it doesn't know how much memory is available for that string. At the moment, the only memory I've allocated implicitly is 8 bytes for the pointer called s. So I'm ready to jot down in memory where I want to put this string, but I never initialize s to anything. Previously, when I wanted to initialize s to something, I could, for instance, malloc some space. Or I could even do something like, I could specify that, oh, let's get out of the pointer business today, and let's actually just say that s is an array of like 1,000 characters, and that would mean I have 1,000 places where I can put that chunk of memory. So turns out there's an implicit relationship between pointers, as we've seen today, and arrays, whereby you can treat one as the other. But for now, let me stick with this model of making clear that I did not call malloc. And so s contains a garbage value, which is like saying put whatever the user types like over like there, somewhere random. It's a garbage value, and that's probably going to cause the computer to crash. Not always, and I don't know what to expect today, but let's try this. Make get /get enter. Let's type in hi exclamation point. I got lucky. It still worked. Let's do something random like just type a lot of characters that will hopefully overflow the buffer that doesn't even exist. Enter. Got lucky. But if I do this again and again, I know ideally that would have made an educational point, but again and again and again, eventually it will probably crash on me. It's certainly incorrect, and I bet we could figure this out with Valgrind if we start poking around with that tool as well. So what's the solution here, or what's really the issue? Well, if we consider where we started, if here's my memory, let me actually put a lot of Oscar the Grouches here to make clear that like before you use memory, it's effectively garbage values. Like who knows what is there? So in my first program, when I created a variable n, I actually used 32 of those bits, or 4 of those bytes, to put a legitimate pattern of zeros and ones to represent the number 50. So that part was good. But when it got to the string version, I allocated space for the pointer, 8 bytes, as I said earlier. But I never initialize s to anything, to malloc, to like an array, like literally nothing. So s's value is literally this sequence of garbage values, so who knows what it is pointing to? There is certainly no memory allocated elsewhere, like in the heap, for whatever the human actually types in. So this value is effectively garbage, and this is the best I could do with squiggly lines. Like, who knows where it's pointing? Certainly nowhere valid. And so in this case, I got lucky. It did not crash, but the more I run the code, the bigger the input it is, odds are this will, in fact, crash ultimately on me. So how can I avoid this? Well, if I go back into VS Code, I could just allocate space myself and say equals malloc of 4. But there's still going to be a danger there, even if at the bottom I do free s, because I only have allocated space for 4 bytes. If the user types in 5 or 50 or 500, who knows what's going to happen? I'm going to overflow my buffer of size 4. I could do this another way. I don't have to use malloc. I can use week 2 stuff. I can, again, as before, just say s, maybe not 1,000, but 4. That gives me an array, which is a chunk of memory, of size 4, but what happens if I overflow that buffer? Like, bad things will happen. And so this is why we still use and would encourage you to keep using getString, because it avoids overstepping the boundaries of any buffer. Like, we literally, as I acted out before, take these baby steps in code, and every time you type a character, essentially we call malloc again and again and again, and it's a little inefficient, but we call malloc as many times as we need to grow enough space in the heap for whatever the human types in, whether it's...
Well, I mean, it's probably going like, you're probably doing some sort of loop and detecting each keystroke as they're inputted and reserving memory upon each keystroke live, right? So you're probably looping, scanning F, and saving if scanf detects something, malloc location proportionate to like size of char, and then keep looping for and keep scanning on the loop for every char input.
1 character for 4,000 or more. It's just really annoying to write out. And in fact, the code is open source, but it's a decent amount of logic just to do something relatively simple. Languages like Java and especially Python make life so much easier with input and output. And we'll get to that in a few weeks' time. All right, so let's transition then to a final topic that's going to set you up really for problem set 4, in which case you'll be exploring something specifically known as file I/O, or file input and output. And we've deferred playing with actual files, where you can save files and open files until now, because you actually do need pointer syntax in C to do that with files. In Python, the world's going to be easier in a few weeks' time when you don't even need that complexity. But for now, we'll explore sort of the idea of file input and output as follows. There are a bunch of functions that come with C related to files. And here's just a short list thereof. But you can kind of infer from the names what these do in code, because they're operations you're familiar with in the real world, like opening a file, aka fopen, closing a file, aka fclose, printing to a file, aka fprintf, and a bunch of others as well. So any function that starts with an F probably means that it operates somehow on files, whether it's text files or binary files with zeros and ones. These functions tend to be involved. We'll see with this how we can now create some of our own files. So let me go ahead and do this. Let me go back to VS Code, and let's make, in the spirit of week 0, my own actual phone book in C. Let's write some code that allows me to save in a file someone's name and number so that it actually persists over time. And I'm going to go ahead and call this phonebook.c. And in this file, I'm going to include, just to make life easier still for today, because we've seen that scanf is not really your friend, we'll use getString again to include CS50.h, standardIO.h, and also string.h, which might be useful. Int main void again. And inside of main, let's do this. Let's first open a file called phonebook.csv. Most of you are probably familiar with CSV files. They're like lightweight they're lightweight spreadsheet files that can be opened in Excel, Google Sheets, or Apple Numbers or the like. It just means comma separated values, or CSV. So I can make a very simple file like this myself, but the syntax is going to be a little new. It turns out, weirdly, in C, there's a data type called file in all capital letters for really no good reason. I'm going to then declare a pointer called file in all lowercase, but I could call it anything I want. And I'm going to set it equal to the return value of calling fopen for file open. And I'm going to specify that I want to open a file called phonebook.csv in, let's say, write mode, quote unquote W. And I know this from the documentation for the function that W means write. And that's why I'm passing it in as the second argument. Now, let's go ahead and do this. I could do string, but we know strings aren't really a thing. So char star name equals getString, and prompt the human for their name. Then let's do char star number and prompt the human for their number. And then I want to save the human's name and number in this file like I'm adding friends to my contacts. Let's go ahead and do not printf, but fprintf, passing in file as the first argument, which is unlike printf. Printf obviously just goes to the screen by default, but fprintf needs to know what file you want to print to. I want to print out a string that looks like a string, comma, another string, and then new line. So just like printf lets you format what you're printing, fprintf lets you format what you're saving as string, comma, string, and then a new line. The last things I'm going to pass in are the values for those placeholders. Store the name and store the number, semicolon. And then lastly, let's go ahead and close the file. So it's not that many lines of code, but this is code enough to prompt the user for a new name, a new number, save. I could run it again. New name, new number, save. And just to make this clear, let me go ahead and do this. Let me open up phonebook.csv, which doesn't yet exist. Let me kind of split the screen here, which if you haven't discovered, you can do by just dragging the tabs up and around so I can see both at once. Let me do make phonebook, enter, /phonebook, enter. And I'll do, how about John Harvard, enter. And now let's see, +1, 949. What's his number? Thank you. And the 2750 spells CS50. So enter. And now notice what happened at top right. In my CSV file, I added a name to the phone book. Now let me run the program again, because there is a bug. I'll put in my name now, and I'll just do, let's see, +1, 617, 495. I think we used 1000 last time. Enter. But notice, John Harvard disappeared. And that's because I chose to write to this file. But there's another mode in which I can write data. I can actually use A for append, which is probably smarter. Let me run my program a third time and put John Harvard back. So John Harvard, enter, +1, 949, 468, 2750. Oh, yes, thank you. Someone caught my mistake before I did. I didn't compile it again. OK, Control-C. make phone book, enter. Now let's rerun /phonebook. All right, here we go. John Harvard, we'll put him back, +1 949 468 2750, enter. OK, that's in there. Let's run it one more time for myself. David Malin, +1 617 495 1000, enter. And now it's indeed appending to the file. So if you've ever used Excel or Apple Numbers or Google Sheets and you're adding rows to the file, or you're literally clicking like new contact on your Android phone or your iPhone, effectively what's happening is Apple or Google wrote code like this to add more and more data to some file. It might not be as simplistic as a CSV file where you're separating the values with commas and just putting it in raw text. It might be some binary file with raw zeros and ones, but it's the exact same idea. And in fact, if I go ahead and try to improve this code, I should note this too. In the spirit of error checking, let me add one additional line before we add one other example to the mix. It turns out that just like malloc, things can go wrong when you try to open files. Maybe it doesn't exist. Maybe there was a typo. Maybe you are, in fact, out of memory. So here too, and for problem set 4 onward, you should get into the habit of checking return values. Don't just assume that you've got a valid return value. Check instead, per the documentation of this function, if file equals null, bad things just happened. Something went wrong, and I should probably just get out of here and return 1 or some other value instead. So again, the lesson today is anytime pointers are involved, from malloc, fopen, and other functions as well, do not trust that they are valid until you have checked whether they are null or not. All right, one final flourish here.
Almost there,
to
guys.
Implement the notion of copying a file as well. We introduced, you might have seen the cp command before for copy files from one to the other. How might we implement that ourselves, even though it's been around for some decades now? Let me go ahead and open another file here called copy.c, or actually we'll call it, we did copy earlier. So, did we? Yes. Let's go ahead and create a new file called cp.c to implement our own version of the copy command. In this file, let me go ahead and include standardio.h, and let me go ahead and include another file, standardint.h, because it's something you'll see in problem set 4. And I'm going to go ahead and in int main, I'm going to use command line arguments now, int argc, string argv as an array, but we know strings don't exist, so technically main can henceforth be written as char star argv, still an array thereof. So we're just getting rid of the word string. And here's how I could open one file and copy it into another. Recall that copy works like this, cp source destination. So it's the opposite of the stir copy function, confusingly. But cp copies the source file to the destination, so you can change the name or give it any name you want. So how might I use this knowledge? Let me create a pointer called source, src for short, and open a file called, well, what should the file be called? Let's expect the user to pass in argv1, whatever the file name is, per the usage at the command line. Then let's open it up in read mode specifically. Then let's go ahead and have a destination pointer called dst for short that equals the return value of opening the second file that the human typed the name of at the prompt, and we'll open that in write mode. I'm not going to do append mode because I want to literally copy everything. I don't want to add to an existing file. And then what do I want to do? I'm going to propose that we do this byte by byte. And there's many different ways to do this. But among our list of functions from earlier are functions like fread for reading from a file, fwrite for writing to a file, as well as fprintf, which prints to a file. But if I actually am dealing with binary data, I might actually want to do this. I might want to declare a variable of type byte, which by convention, especially in the Windows world, is capitalized as byte. Give me one variable of type byte. And let me do this. While I read from the file, passing into that byte a byte from the file. So give this function the address of that byte so we can go put 8 bits in it. Then let's read in the size of a byte, which I could just write as 1, but I'm going to keep it dynamic. I'm going to read one such byte at a time, and I'm going to read from the source file. And I'm going to keep doing this so long as the return value is not 0. This is a mouthful, but allow me to just stipulate for today's purposes that line 11 just starts a while loop that iterates over the file called source, byte by byte by byte by byte, from left to right, top to bottom, so to speak. And how do I save each of those bytes to the destination file? Well, I can do fwrite, passing in the address of that byte so we can go to the location, the size of it, so it knows how big it is, how many there are, which is still 1, but send it to the destination instead. And then at the end of this code, let me hide my terminal for a moment. Let me go ahead and close, for instance, the destination file, and let me go ahead and close the source file. And ultimately, I think this is enough to, again, iterate over all the bytes in the file, 1 byte, 1 byte, 1 byte at a time, and write them byte by byte by byte. And minor tweak. Technically, because I want to do this literally, there's no text involved, there's no Unicode. I just want this to be a raw copy of bytes. Technically, I can specify read the file in binary and write the file in binary. Don't try to do any kind of interpretation of characters. Treat it as raw zeros and ones. And just so you've seen it, technically in C, there is no such thing as a data type called byte. This is, again, a thing in the Windows world, and we will give it to you in problem set 4. But I can actually create a type using typedef. I'm going to have it be equal to something called uint8t, where that just means unsigned 8-bit integer. But more on that some other time, or never, perhaps. But for now, that just gives me a byte of 8 bits in a manner consistent with what Windows computers do. And if I didn't mess this up, let me open my terminal window, make cp for make the copy program, .cp. I want to run .cp, so it's my version of the copy command, not the built-in system one. Let me go ahead and copy a file like, what was the file we started with? Addresses.c. And how about we'll call this backup.c. And if I open up addresses.c here, we'll see the file with which we began class earlier. If I open up backup.c, we'll see exactly the same file. If I hold them side by side, these happen to be text, but they could have just been raw zeros and ones. I've indeed implemented the cp command correctly in this way. Now, how, though, does this loop work? Let me go back into cp.c. Recall that I had this loop here. Let me close these other files. There was this loop that somehow just knew to advance to the next byte in the file, even though there's no +1, there's no for loop explicitly. It's just kind of reading and reading and reading until fread returns 0. Well, the reason for that is that these file reading and writing functions behave a bit like a YouTube video or a Netflix video, whereby once you start reading from them, like watching them, the sort of cursor advances from left to right. So as soon as you read a byte, the file itself keeps track of where you are in the file. Kind of like an old school cassette tape. Once you start playing it physically, the device is moving, so it knows where to read the next bytes from and where to write the next bytes to. And this is all going to be germane as we introduce, ultimately, a specific file format this week in problem set 4 known as a bitmap file, or BMP for short. In the world of bitmap files, you'll see that you can represent images like this, but these images are really just going to be a grid of pixels, top to bottom, left to right. And among the goals for this week is to implement some Instagram-like filters via which you can actually manipulate these images. So for instance, among the filters you'll implement is first one that converts any image, even a photo you yourself took, into black and white by throwing away color information somehow and just retaining some form of grayscale. You'll implement, and it's a bit hard to see on the screen, but a sepia tone, sort of an old school photographic style. You might be able to invert or flip the image on its axis here. So I've just reversed the sides of the bridge. Same photo, just flipped around in the computer's memory by moving like these bytes over here and these bytes over here. Or if you really are feeling more comfortable, you can do edge detection and write, no, I said that wrong. Or if you're feeling really, no, wait, everyone has to do this. Sorry, let's stick the landing. We have like 1 minute left. So what you'll also be challenged to do is blur the image too, whereby you're going to make it look fuzzier by sort of combining pixel values so that it's not quite as crisp as it originally was. And if you're feeling really comfortable, you can even do edge detection, whereby you can figure out where the outlines of physical objects are on the screen by writing more sophisticated code optionally to render images such as this here. So ultimately, this whole week is going to be about file input and output, recovering images that might have been deleted or corrupted as well. But we thought we'd end on a final pointer note. This is another one of these comics that now computer scientists should be able to understand the humor of, hopefully. OK, lots of laughter. All right, that's it for CS50. We will see you next time.
Woo! All right, we finished. Oh, that was a long one. That was long. Thank you guys so much for sticking with me here. And thank you guys so much for sticking with me throughout this lecture. We watched the Harvard CS50x 2025 Lecture 4 on memory.